Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 10 for our MCAT Physics and Math playlist. And this chapter is titled Mathematics. In this chapter, we're going to cover 4 main objectives. The first objective is titled Arithmetic and Significant Figures. We're going to begin this objective by understanding scientific notation. This is a way to represent very large or very small numbers in a concise manner. Then we're going to learn about significant figures. And finally, we will discuss estimation techniques to quickly approximate solutions, especially since there are no calculators on the MCAT. The second objective is titled Exponents and Logarithms. In this objective, we're going to explore the rules and properties of exponents, which form the basis for understanding logarithmic relationships. We're also going to discuss the difference between common logarithms, which use base 10, and natural logarithms, which use the mathematical constant e. The third objective is about trigonometry. So here we're going to define key trigonometric functions such as sine, cosine, and tangent, and we'll also discuss their relationships. Last but certainly not least, we're going to cover problem solving. So in this objective, we're going to focus on problem solving techniques that tie all of these concepts together. This includes understanding relationships between variables, performing unit conversions, using dimensional analysis, and solving algebraic systems. So with that introduction, let's go ahead and get started with Objective 1. To start, scientific notation is a method that's used to express very large or very small numbers in a way that simplifies calculations and ensures that numerical information is communicated effectively. In science, we often deal with measurements and values that span a huge range, from the diameter of a cell to the distances between stars. And writing these numbers in their full form isn't always efficient. Scientific notation solves this problem by representing numbers as the product of 2 components, a coefficient, also called the significand, and a power of 10. Now the coefficient must be greater than or equal to 1 and less than 10, while the exponent shows how many places the decimal has been shifted. So for example, let's write 87,000 in scientific notation. We're going to start by identifying where to place the decimal point to create a number between 1 and 10. So right now our decimal point is right here. Where do we want to move this decimal point to get a number between 1 and 10? It's going to have to go between 8 and 7. This gives us 8.7, and that meets the criteria for a coefficient. Next, we want to determine the exponent value for the base 10. Scientific notation uses a base of 10 raised to an exponent to account for how many places the decimal point has been moved. Here, we've moved the decimal point 1, 2, 3, 4 places to the left. Since the decimal was moved to the left, the exponent will be positive, and specifically the exponent is going to be positive 4. So putting it all together, 87,000 is written in scientific notation as 8.7 times 10 to the power 4. Let's try another example. Let's write 0.00056 in scientific notation. Again, our first step is to identify where to place the decimal point so that the number is between 1 and 10, so that the coefficient is between 1 and 10. In this case, we want to place our decimal point between 5 and 6, giving us 5.6. This meets the criteria for the coefficient. Next, we need to determine the exponent for the base 10. To do this, we have to count how many places the decimal point was moved. So starting from the original position, the decimal needs to be moved 1, 2, 3, 4 places to the right. Since the decimal point was moved to the right, the exponent will be negative. Specifically, it's going to be -4. Putting it all together, 0.00056 is expressed as 5.6 times 10 to the -4 in scientific notation. So this standardized format not only reduces the risk of mistakes when handling extreme values, but it also makes it easier to compare magnitudes across different quantities. In addition, scientific notation becomes especially helpful when we're working with significant figures because it clearly shows which digits are meaningful, and that contributes to maintaining accuracy in calculations. With that being said, let's transition to significant figures. Every number in science reflects the tools or methods used to obtain it, and significant figures help ensure that calculations don't introduce false precision or overlook uncertainty. Significant figures include all of the certain digits in a number, plus the first uncertain digit. To ensure that we handle this appropriately, there are rules we need to follow. So let's go over the rules for determining the number of significant figures. Rule number 1 says, all non-zero digits are significant. So in a number like 863, this number has 3 significant figures because each of these non-zero digits are significant. Rule number 2 says that any zeros between significant digits are also significant because they serve to define the number's value. So in a number like 5042, this number has 4 significant figures because the 0 in the middle is also considered a significant figure. Now, rule number 3 says zeros at the beginning are not significant, and rule number 4 says zeros at the end are significant if there is a decimal point. So let's elaborate on these two. Rule number 3 deals with leading zeros. So zeros that come before a number. For example, 0.005. Here, these leading zeros are not significant because they're just placeholders. So this number only has one significant figure. However, trailing zeros is a different thing, and that's what Rule 4 is covering. Trailing zeros in numbers with a decimal point are significant. So if we were to look at a number like 0.05430, this number is going to have 4 significant figures. This trailing zero is significant, and it is only significant because there is a decimal point. Now, significant figures also play a very important role when we're performing operations like multiplication, division, addition, or subtraction. And there are 2 rules we need to consider here. The first rule deals with multiplication and division, and the second rule deals with addition and subtraction. For multiplication and division, the result must be rounded to match the number of significant figures in the least precise measurement. So for example, if we multiply 10.7, which has 3 significant figures, by 8.1, which has 2 significant figures, our final answer must be rounded to 2 significant figures. This ensures that our result doesn't imply greater precision than our initial measurements. In addition and subtraction, the rule changes slightly. So here the result is rounded to match the least number of decimal places in the measurement. So for example, when we're adding 12.56, which has 2 decimal places to 0.7, which has 1, our final answer has to be rounded to 1 decimal place to match the precision of 0.7. So that means the sum, 12.63, needs to be expressed as 12.6. With that, we can move into our last topic in Objective 1, and that topic is estimation. Estimation is a valuable tool for simplifying calculations, and this technique is obviously useful for the MCAT because calculators are not allowed. Now, on test day, much of your math is going to be determined by the answer choices provided. If the answer choices are very close together, then there's going to be minimal opportunity for rounding. But if the answer choices are very far apart, then rough estimations will get you the answer you need. Dealing with addition and subtraction is pretty simple. You just have to be a little bit considerate about how you round. But there's a couple of things you should keep in mind for multiplication and for division. For multiplication, if one number is rounded up slightly, then the other should ideally be rounded down to prevent overestimating the result. As for division, if you round the numerator up, you should also round the denominator up. Why do we do this? Well, because this keeps your approximations logical and it keeps your final answer close to the actual value. Now we're going to tackle a practice problem to see this in effect, but I also want to pause for 1 second and go over a couple of fun multiplication tricks that I learned when I was doing number sense as a kid. These are really fun, I promise, and you can use these tricks to impress your loved ones. So the first trick applies to multiplying 2-digit numbers by 11, provided that the sum of the digits is less than 10. So to do this, you're simply going to split the 2 digits apart and place their sum in the middle. So let's do an example. Let's say we want to multiply 17 by 11. We're going to go ahead and take 17. The sum of 1 and 7 is equal to 8. This is good. That means we can do our trick on this multiplication. To figure out the answer, we're simply going to take 17. We're going to split it apart, and then we're going to put the sum of 1 and 7 in the middle. So that's going to be 8. That means 11 multiplied by 17 is equal to 187. So that was quick multiplication. The second trick is for squaring numbers that end in 5. These squares always end in 25, so you only need to determine the digits that precede the 25. And there is a very easy way to do this. So let's do an example. All right, let's try to figure out 25 squared. The answer to this is always going to end in 25, so we can go ahead and write this down. Then what we're going to do is we're going to take this first digit, 2, and we want to multiply it by 2 plus 1. So the digit itself plus 1. Essentially what we're doing here is 2 times 3. This is equal to 6. So 25 squared is equal to 625. And this works with the square for any number that ends in 5. I want to do another one because this one's my favorite. Let's do 45 squared. This is just going to be 25 in the end. And then it's going to be 4 times 4 plus 1. So 4 times 5, which is 20. 45 squared is 2025. Now, our last and final trick works for 2 numbers in the same tens region whose last digits sum to 10. So for example, let's multiply 33 by 37. So you notice these 2 numbers are in the same tens range, and then the sum of their ones digit add up to 10. So to figure out the answer for this, it's really easy. We're going to multiply the ones together. 3 times 7, that's equal to 21. These are our ending digits. And then to figure out the number in the front, we're just going to take 3. All right, we're going to take the tens digit, in this case 3, and then we're going to multiply it by itself plus 1. So 3 times 3 plus 1. So this is 3 times 4, which is equal to 12. So 33 times 37 is equal to 1221. So these are just 3 quick tricks to do multiplication really fast. I hope you enjoyed that. This was a little fun tidbit I really wanted to add. So with that being said, let's jump into a practice problem. This problem says, estimate the value of 15.4 divided by 3.80. Now, estimations in division should be made by shifting both numbers in the same direction. Now, it's usually easier to adjust the denominator first to simplify calculations. So here I'm going to round the denominator to 4. We should keep this in mind when we round the numerator. Again, estimations in division should be made by shifting both numbers in the same direction. So since I rounded the denominator up, I should round the numerator up as well. What number can I round the numerator up to make the division by 4 easier? The answer here is 16. 16 divided by 4 is a really easy calculation, and we get 4. Now, the actual value of this division process is 4.05, so you notice we did our estimation really well because the value we got is really close to the true value. With that, we can go ahead and move into objective 2. The second objective goes over exponents and logarithms. Exponents are a convenient way to express repeated multiplication. For example, instead of writing x multiplied by x multiplied by x 3 times, we can instead write x raised to the power of 3. Here the base is x, and the exponent indicates how many times the base is multiplied by itself. Now, exponents follow specific mathematical rules that simplify their use in calculations. We're going to start with the zero exponent rule. This rule states that any base raised to the power of 0 is equal to 1 as long as the base is not 0 itself. The second rule is called the product rule. Here, when you're multiplying 2 terms with the same base, you add the exponents. For example, x raised to the power of a multiplied by x raised to the power of b is equal to x raised to the power a plus b. The third rule is the quotient rule. Here, when you're dividing terms with the same base, you subtract the exponents. For instance, x raised to the power a divided by x raised to the power of b simplifies to x raised to the power of a minus b. Next up, let's talk about the power rule. So for this rule, when you're raising a power to another power, you go ahead and multiply the exponents. So for example, x raised to the power of a and then raised to the power of b becomes x raised to the power of a times b. The fifth rule is the power of a quotient rule. So when a fraction is raised to a power, the exponent applies to both the numerator and the denominator. So for example, x divided by y raised to the power a becomes x raised to the power of a divided by y raised to the power a. What about negative exponents? A negative exponent means that the reciprocal of the base raised to the positive version of the exponent. So for instance, x raised to the power of negative a is equal to 1 divided by x raised to the power of positive a. And then our last rule is the fractional exponent rule. So fractional exponents represent roots. So x raised to the power a divided by b is equal to the b root of x raised to the power a. Building on this, on the MCAT, you may be expected to calculate approximate square roots. A square root is the value that, when multiplied by itself, gives the original number. So for example, the square root of 9 is 3 because 3 times 3 is equal to 9. Now, when you're estimating square roots of numbers that aren't perfect squares, one method is to determine which two perfect squares the number lies between. So for instance, to approximate the square root of 50, note that it falls between the square root of 49, which is 7, and the square root of 64, which is 8. So this tells us that the square root of 50 falls between 7 and 8, and it leans more towards 7 because 50 is closer to 49 than it is to 64. Now for this strategy, it might be useful to be familiar with the square values of integers from 1 to 20. But another useful method for simplifying square roots actually involves dividing the given number by known perfect squares and then rewriting it in terms of smaller components. So for example, let's consider the square root of 180. To simplify this, we can start by identifying perfect square factors of 180. The number 180 can actually be divided by 4, which is a perfect square, and that yields 45. This means that the square root of 180 can be written as the square root of 4 multiplied by the square root of 45. Next, we can simplify the square root of 45 by breaking it into the square root of 9 multiplied by the square root of 5. So the square root of 9 is another perfect square. So from here, we know the square root of 4 is 2, the square root of 9 is 3, and now we have 2 multiplied by 3 multiplied by the square root of 5, and that gets us a final answer of 6 multiplied by the square root of 5. So in short, this method allowed us to break down square roots into manageable pieces by systematically identifying and using perfect square factors. Now we can move into discussing logarithms. Logarithms are the inverse of exponents, and they follow a set of mathematical rules that make them especially useful for simplifying complex calculations, particularly when we're dealing with exponential relationships. While exponents answer the question, what is the result of multiplying a base by itself a given number of times? Logarithms answer the reverse question, to what power must the base be raised to obtain a specific value? So with that being said, let's cover logarithm rules. The first rule says that the logarithm of 1 is always 0 regardless of the base, because any number raised to the power of 0 equals 1. The second rule states that the logarithm of the base itself is 1, because any base raised to the power of 1 equals itself. The third rule says that the log of a product is the sum of the logs of the factors. So in other words, log A times B is equal to log A plus log B. The fourth rule states that the logarithm of a quotient is the difference of the logarithms. So for example, log A divided by B is equal to log A minus log B. The fifth rule states that the logarithm of a number raised to an exponent is equal to the exponent multiplied by the logarithm of the base number. So in other words, log A raised to the power of B is equal to B multiplied by log A. And then the last rule is the reciprocal rule of logarithms, and it explains that the logarithm of the reciprocal of a number is the negative of the logarithm of the number. So log 1 over a is equal to negative log a. Another important aspect of logarithms is the distinction between common logarithms and natural logarithms. Common logarithms have a base of 10. Natural logarithms, on the other hand, use a base of e, where e is Euler's number, and that's approximately 2.718. Natural logarithms can be converted to common logarithms using this formula right here. This formula says that log base 10 of x is approximately equal to the natural logarithm of x divided by 2.303. Now, in addition, logarithmic expressions involving multiplication by powers of 10 can also be simplified in a really interesting way. So for instance, log of n multiplied by 10 raised to the power m, this can be broken into log n plus log 10 raised to the power m. Following our logarithm rules, log of 10 raised to the power m simplifies to just m. So now we have log n plus m. Further, because n is a number between 1 and 10, its log will be a decimal between 0 and 1, because log of 1 is equal to 0 and log of 10 is equal to 1. The closer n is to 1, the closer n will be to 0. And the closer n is to 10, the closer log n will be to 1. So then, as a reasonable approximation, we can write that log n multiplied by 10 raised to the power m is equal to m plus 0.n. This is going to be really useful in pH calculations in the chemistry section. So keep that in mind. For now, we've completed objective 2. We're going to go ahead and end the video here. In the next video, we're going to pick up at objective 3, where we're going to discuss trigonometry. I hope this was helpful thus far. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.